Hello and welcome. In this video, we're going to continue with our looking at different algorithms. And so this is a part of the video series that came before this. And so in the previous ones, we looked at writing functions like factorial functions or recursive functions with our Fibonacci sequence, or we looked at binary search. And so what we're going to do is we're going to take a look at those speed performances of those different algorithms. One thing that you do in computer science, a lot of people who study computer science go on to become software engineers. The engineering part of software engineering is actually going and tinkering with your program to make it the most suitable solution for the problem that you're trying to solve. Meaning that if you want a big program, but you're okay with it being slow, but easy to use, then that's what you build the solution for. If you need a program that's fast, you make it small. You try to trim out the code to make it the most performant that you need for your particular solution. So here's the chart that we would often look to for a quick way to reference this. This is not my own chart. This was by BigONotationCheatSheet.com. So thank you to Eric over there for making this. But we call it Big O Notation. And what it is just a way to think about the code and the number of operations or time it's going to take to complete a program, complete a little snippet of code, given a certain number of elements as input. So given a certain amount of inputs, how long is it going to take the program to solve all those to give you your outputs? So here we look at operations and elements, and we see the different O and the different notation next to it. So I'm going to explain all these things and what they mean. And to do so, we're actually going to be using a library called Plotly. And so if you just go to Google and type in Plotly.js, Plotly is actually a great library. There's a version for Python as well too. And so there's a JavaScript version, there's a Python version, and they have their own website. It's free to use. And what we can do is actually go, is this a JavaScript version? Yeah, it is. And we have basic charts. There's also different charts. And they're super simple. Maybe I'll make another video on like how to make different charts here, but we're just going to use a scatter plot because it becomes with a line already built in. And this is how we would make it. So it's actually really easy. We're going to set it up together, and then our output will look like this. So we're going to build our own version of this chart. All right, so we can get started with that. And then we'll go into each of the algorithms and see how they would perform with a certain number of inputs. And we're going to put in a lot of inputs too. We're going to try to mimic this as much as we can, but actually it takes quite a few inputs, and the website I'm using, REPL, doesn't have a lot of, it doesn't allocate a lot of CPU time. So we can show a small deviation, but to really get these curves here, you'd have to put in a lot of operations, and you'd have to allow for calculation time, and we just can't do that. So you'll see this, but you just won't see the nice curve when we get to the danger zone over here. All right, so let's start off by going to our HTML file, and we should have our body script tag should already be there. Does not, make sure you link to your JavaScript file. And then to add Plotly CDN, there is a get started there as well too. Actually, we can just use that one. We can just use the get started for Plotly. And then it tells you Plotly CDN. And so we just want to link it right here. So I'm going to copy that. It says to put it in your header, but you can actually put it in your body, or as long as you add it. Make sure that you add it before your JavaScript file, your script.js. Otherwise, this will not work. They have to go one after the other. And then it also tells you that you have to set up a div with a name, and you can size it. I'm not going to size it. But up here, we would do div, and we set an ID for that div, say chart. And that's it. We can close that div. That's all we need to do to get our charts inside of our program. Now we can go to our JavaScript file and make sure I'm zoomed in enough so you can see it. And REPL comes nice with a little web page down here. So we're going to see our stuff displayed. And what we have to do is we have to set up our our charts a little bit. So our topic is going to be algorithm speed, oh boy, and Big O notation. Okay, so we use what's called Big O notation to classify algorithms. And just a heads up that we classify algorithms by the worst case scenarios. So this isn't like the Guinness Book of World Records of like algorithms and like their when they're at their best. You know, this isn't the Olympics of algorithms. In computer science, we judge an algorithm by its slowest performing time, worst case scenario. And we you know, every now and again, maybe a program searching will come up with the answer in the first index that it searches, and that's great. But if it doesn't, how long is it going to take to find an answer? So we judge it by its worst case scenario. Okay. So we're going to take a look at that, and we're going to graph those. So to graph them, we'll have to set up the chart, which is we're going to initialize variables, and we'll set up our chart. The chart actually takes, if we want to do a scatter plot, we have to basically set up a scatter plot here. This is what we need to do. We need to set up a XY values. We say scatter, and then we basically say what data we want to plot, and then we do plotly new plot. So we'll do all that. Okay, so let's set up we'll set up constants, and we're going to do a couple different algorithm speeds. So the first one's going to be constant. So we'll say const data equals X, and we'll set up an empty array initially. Y, another empty array. Type, be scatter. And name, for this we'll say constant. And we'll say big O of 1. And we'll change that throughout. Because I don't want to have to rewrite this numerous times, I'm going to copy this. I'll zoom out so you can see. I'm going to copy this const data a couple of times. And I'm going to do is I'm going to go in the second one. The second one's going to be linear data. And I'll change the name to linear. And that's big O of n. Big O of n, so just big O, and then inside the parentheses put n. The next one we'll do is quadratic. That's right. Data. And so this is just the chart. We're not actually quadratic. And this is just the chart. So we'll actually do the equations later on. N. I'll do n. The up caret is the, on my keyboard, it's above the letter 6. So I do shift 6, and that gets me that. Quadratic, big O of n squared. And then after that, we have exponential. Data. Exponential. And exponential is going to be 2 to the power of n. And n, what we're referring to here is the number of items. Okay, so we look at big O of n. So given a, you know, think of like a list of names of, or a list of numbers. It could be just random numbers, just 100 random numbers. 100 would be essentially the number of items going in. So like I said, we'll see that when we actually write out the equations for this. But let's go through the rest of this and set this up. So exponential data, and then the last one is going to be logarithmic data. And I'll change this to logarithmic. And that one's going to be big O of log n. All right, and then the Plotly also requires we set up the, let's see, does it say? Plotly CDN, get started. It actually says the config file, but basically we can pass in a configuration file that, or a configuration object that allows us to customize it. So let's do const layout equals, and then we can do title, algorithm speed, x-axis. We label the x-axis as title. We could do number of items that we enter. And then we can do, after that, make sure you add a comma, otherwise it's not going to work. Y-axis, title, we can put running time complexity, and we'll judge that in milliseconds. So we can do parentheses ms. All right, and then that's it for that, I think. Okay. So yeah, what we did is we just set up the chart using the Plotly. And this is all the stuff that you get off their website. So it's not like something I just innately knew. I went and took a look and see what they said to set it up, and through some trial and error, I figured out what I was missing here. Okay. All right. So the next thing we're going to do is we want to create a couple different tests. And in order to generate the scatter plot, we're going to need to generate the number of items at the bottom there. And so we're going to run the tests on a couple different functions, but we're going to increase the size of an array. So an array is a great example of just a list of items, and performing an operation on each item in the list. How long is it going to take to compare everything in the list, to sort everything in the list? So we're going to need an array of different sizes. We could create those different sizes, but we're going to talk about some pretty big numbers here. We're going to go up to 100 million items in the array and see how it does with different calculations. So I want something that I can make flexible. So what I'm going to actually do is I'm going to set up a function here that handles the creation of the array. Create random array, and we'll pass in the size that we want and the max number that we're going to want as well too. And inside there we can do const. We can just set up the data array as an empty array, and then we're going to fill it up, and then we'll return that at the end. So we can do for let I equals 0. I is less than size. I plus equal 1. Okay, that will go through, and we can pass in the parameter size and basically make it as big as we want it. And then we can do data I, so we'll get the index position inside the array, and do math dot round. And then let's do math dot random. And that will get us a number 1 to 0. So let's times it by 10 to make it an integer. We'll do plus 1. Actually, we don't want to times it by 10 because that'll give us a max of 10. Let's do max as the variable there. So math.random 0 to 1 times the max values. Say we have 100, then it would be 0 to 1 times 100. So the max number would be 100. Plus 1, yeah, we can get rid of that. Okay, so math.random times max. Okay, that'll set up our array and fill it with the max number of things we want. And at the end, let's return data. We'll return that array so that we can use it inside of our programs. All right, and the next thing we're going to do is actually set up a way that we can update X and Y inside each of these different objects. And so the idea is that we have a chart. We're going to need a way of updating those charts as we write our functions. So let's create a new function called update Y, and we'll pass in a chart name, meaning that up here we have logarithmic data, exponential data. We want to be able to customize it so we can go to each one of these and then access the X and Y property of each and then customize it. So then the next thing, I guess, would be we have our chart name, and then we'll pass in a value as well too. And what we're going to do, we can do something easy. We can just do chart name. So we'll get that when we pass it in. We go to the Y property, and it's an array, so we can push the array with a value. So basically, we're going to add, if we do update Y, we're just going to add in a value. So if it's 0, we're going to push the array. We're going to add it on. And JavaScript push is going to just add that item to the array. So we can do that. There's other ways you can do it. You could do the array like plus equals. I think push is probably just the easiest because it doesn't. We're going to be adding it on to the end. So in that case, that's what push does. It adds on to the end of the array. So as we call the functions, we could just simply call update Y and just add those values. Let's also do an update X. So function update X, chart name, and we'll add value. And then we could do chart name, same as above, X push value. Okay. And I think that's all we need for the chart. To actually get the chart up and running, it's actually relatively easy. We just need to toss it at the end. It's probably the easiest way to do this, but we just do const chart. We set up an array. So this is the const data, linear data. These are all the objects we have above here. We're just going to pass them into Plotly as the things that we want to add. Quadratic data, exponential data, logarithmic data. Okay. And after that, we can do Plotly.new plot. We pass in the name of the chart. This is it from the div. This is this right here. Div chart that's the first thing. And then we pass in the data. If we want to make it clear what that is, I don't want to mess it up. If I have it up here, chart data, if I do anything here, chart name, chart, no, it's okay. We do chart data. And then layout is the config file that we set up here for just the layout of the actual entire chart. Okay, so that was a lot. You could make it simple if you didn't, we're doing quite a bit in the same file. So if you just want to set up a simple XY coordinates, you could just do that, but by passing in numbers here, and that's your XY pairing. So as long as you have an X value and a Y value, if there's not one given, I think it just defaults to 0. But yeah, you just pass in the pairings here like you would on a coordinate graph, and like a regular scatter plot, and it'll create your graph for you. So it's actually super easy to create. And we do run, it should actually create the graph for us. Let's open a new tab. See what's going on here. Unexpected token on line 50. What did I do? Line 50. Oh, I got math dot round, math dot random times max. Yeah, I don't need that extra there. Okay. There it goes. All right, so we can refresh the window. And all right, cool. We see our scatter plot here, all set up and ready to go. Okay, let's go back and let's start writing on our functions to test. So the first one we're going to test is we just have to make sure that our chart data is down the bottom. So I'm going to make some spaces down there because it will update once we run on all our functions. All right, so let's go to, we have our random numbers. We're good. Okay. So the first one's going to be constant time. And what this is a function, or come on, there we go. So this is a function that constant time. We pass out a number of items. And let's set up a const array equals create rand number array, number of items, and we'll make the max number 100. So what this is going to do, a constant time, is it's going to take the same amount of time no matter how big the input is. So in our graph over here, it's way down the bottom. It's O of n, all right? It should be O of 1. So this is like stuff like your print statements, finding the first element, which is what we'll do here. This is a very efficient algorithm. It's ideal if you can get this way, but it's kind of hard because, well, it's not hard. It is what it is. Meaning that you're not gonna, every program you write is not gonna be a constant time. Basically go into an array and get the first thing. That's always, the first thing's easy to find, so it's always going to be that. So how do we measure performance? What's kind of cool is we actually do const start time is going to equal, the browser has something, JavaScript has something built in called performance. And what it'll do is we can start the time, start to measure performance now. And this is different than like time, because performance is going to measure down to like numerous decimal points. It's going to get pretty exact in terms of its time calculation. Let's set up our first is just going to go inside the array and get the first element out of the array. And then we can do const end time equals performance dot now. And then we can do const total time equals end time minus start time. Okay, that will calculate the difference for us. And then let's go through and actually I can console.log total time so I can show you exactly what's happening here. And let's run constant time 10. And so what we're doing is we're going in and number items. Why did I do that? Num items. Sorry, let me change that. Num items. So yeah, all right. So our array is going to have 10 items inside of it. from 0 to 100. So let's run that, and it won't plot anything. But if we go and take a look at the console, actually, no, I lied. We have a console built in. Really handy. Console log total time. Should console log total time. Why is it not console logging total time? End time minus start time, first array, performance. Is it not doing because it's not built in? Take a look. Okay. All right. There we go. All right. Cool. I don't know if you can see that on mine, but on yours, if you're using REPL, it apparently doesn't get you the actual information. It doesn't have performance built in. Not too sure, but the browser does. And so mine, yeah, it's kind of hard to see. There we go. Mine has 0. What does that mean? 0 is the running time complexity in milliseconds, meaning it took 0 seconds to do that calculation. So it took 0 seconds or 0 milliseconds to create a random number, or actually that was created before we started calculating. So we didn't include this in the calculation time. Suppose you should, but we're just trying to calculate a constant, and that would actually increase our calculation time. So we see first array. Yeah, so how long does it take to access the first item in the array and assign it to a variable? It takes 0 seconds. And we actually can see what that is. First, let's run it one more time. And we'll go back and refresh here. And we see that same side attribute. Okay, we're not going to worry about that. All right, so we see the first item on the array is the number 40. If we refresh it, we see the number is 52. So it's taking 0 seconds to find that element in the array. That's constant time. And what's neat about it is actually, let's update our graph, update chart. And to do that, all we have to do is call our two functions we set up, update x, and we can pass in const data as the chart we want to update. And let's pass in the number of items for the x-axis, and then update y with our calculation time, const data total time. We'll pass that in. And then what we can do is we actually can call constant time a couple of times. So I'm going to take this and I'm going to copy it a bunch of times. And so let's go through. Yeah, let's add in 100 times. Let's add in 1,000 times. 10,000 times. Let's see, that's 10,000. So we got 10, 100, 1,000, 10,000, 100,000. So this is the size of the array that we're creating. 1 million, we'll do that. So let's do that. So 1, and then we need 1, 2, 3, 4, 5, 6. That's our 1,100,000. Should have an extra one there. Okay. And then let's do one more. Let's do 100 million. So these are arrays of different lengths. So we have some arrays that are 10. The first one is 10. And then we increase it all the way up to 100 million items in the array. Okay, let's run it. And we can refresh. Oh, I'm going to speed this up by getting rid of our console log. So get rid of your console log, comment it out, and it's going to speed that right up instead of trying to console log 100 million items. So let's run it again. Take a minute to calculate. Okay, so what do we see here? Actually, it's such a low time that it's graphing it out for us, but we see the first one comes in at, 9,000th of a second. So yeah, that's pretty nuts. And then it actually goes down to, maybe because it's cached. Yeah, I bet the browser's caching the data. And so we're seeing that. Actually, maybe not. I don't think I have the cache turned on. To check, otherwise your graph might be kind of wacky. The browser is going to try to cache it. So if I have my network, my admin tools here, my developer tools, I can actually go to, let's see, our settings in the right here. And in settings, you want to make sure that you have the option here for disable cache. Here it is. Under network, disable cache while DevTools is open. Make sure that's checked off and your browser won't cache any of the data so you can see these calculation times. So this is constant time. It's happening on such a low scale or small scale that in comparison to everything else that it's happening relatively quickly. So we can find out the index position of 100 million items or assign that variable in fractions of a second. So that's really fast. Okay, so that's constant time. Let's go to the next one is linear time. And for linear time, you could think of linear time as a big O of n. And as the number of items in your array increases, the time it's going to take it basically has to go through each one individually. So as the size of your array increases, the number of calculations needed to complete your program is going to increase as well too. So basically an array with 1,000 items will take exactly 1,000 times longer than the item before it. So we should see a line going up. So let's set up our function linear time and items just as above. And a lot of the stuff's going to be the same. So I'm going to actually grab we can grab the entire function if you like. And down here, I'll just paste it again. Delete const. There we go. So linear time, number of items, we'll create an array just the same. Max number 100. And then the only thing we'll change here, I'm going to make a note. This is the main code. We're going to delete the const first array. We're going to delete that. And we're going to have to change const data down below here to linear data. Linear data. All right, so the main code between the start time and end time, let's add a for loop. For I equals 0, I is less than the num items. Yeah, that's right. Wait, is that what I did above? I suppose you could do... No, actually, I didn't do that above. Num items. Yeah, we'll do num items. You could do array.length. That's fine, too. I suppose that's what people are more familiar with. Array.length. So however that long that array is. And then what we can do is, let's see, we'll add the I plus equal 1. So we'll iterate that. And then let's do array. Let's go to each array item. I, the value of whatever position it's on, I. And let's do plus equal 1. So we're just going to add 1 to every item in the array. Okay, so how long is that going to take? I'm not going to console log anything, so we'll get rid of that. But we can update the chart. That'll be fine. Yeah, so we have an array that we create, number of items, and then we increase it by 1 every time. So let's call that. I'm going to go up here to my calls, to a constant time. I'm going to grab them down here, and I'll just change constant time. Actually, I'll do linear time once. Linear time. And I can just take this and copy it to each one. Whoops. Okay, so we have our constant time and linear time. We're going to run both of them. We'll see what happens. Click run. You can refresh this page. We'll get some calculations going on here. Delete the other one I had. Make sure there's not an error. Oh, we do have an error. 993. What did I forget? Oh, I have a comma here instead of a semicolon. There we go. All right, I was just waiting here to calculate. Okay, there we go. All right, now we're starting to see that. All right, so we said linear time. A linear time equation should have a growth that is proportional to the increase in the number of items being entered into it. So here we start off with 0. We see a little bump at the beginning. I don't know why. Maybe just an initialization of variables. But in any case, I mean, we do see this linear growth going right up as the number of items input goes in. And why is that happening? Because the array is growing in length, and all we're doing is going through each item in the array and increasing by 1. So it's going to go up. It has to go up, right? Because as the array goes, it's going to take longer to go through the array. So that's good. But we see constant time is happening at a fraction of a second, and linear time is growing substantially. So and we have our other points down here. Okay, so that's linear time. The next one we're going to do is quadratic time. And this is big O of n to the power of 2. Big O of n. So you take the number of items that you have and you square it. You're going to see a growth similar to linear time. There's going to be a line going straight up, but it's going to happen at a higher rate. So we're going to see a higher rate of climb for the quadratic time because you're squaring it. So what type of program is quadratic time? Well, we've all done it. You write a program where you have a loop inside of a loop, and if you do that, you're now in quadratic time. And it's not completely danger zone. We see quadratic time here. This shows it as danger zone. I suppose these elements here, we're not going to see, like I say, we're not going to see this type of curve just simply because we don't, maybe we don't have enough complicated operations that we're going to put into it. We're going to see them grow at different rates, that's for sure. And we already saw it with big O of n versus big O of 1. So constant versus linear. Quadratic, we're going to see go up, but we're not going to see such a dramatic curve here. I suppose if you had more complicated code, you probably would see that. But yeah, any loop within a loop is going to cause this. And if you have like three nested loops, every time you nest a loop, you're increasing the calculation time. So let's go up here and let's actually copy everything we did for linear time, because we're essentially going to reuse it. And make sure, you make sure you're putting it above the chart data, otherwise it's not going to work. All right, and I'm going to zoom out so you can see. There's now I have essentially 2 linear times. One under that. I have linear time above, and then I have quadratic down below that has linear time. We're going to change all this stuff to quadratic time. Just make sure you're changing the right stuff, otherwise you're going to be missing some information. You're going to be missing your quadratic line. So let's change this to quadratic time. Number of items remain the same. I'm going to get rid of my main code for right now. I'm going to put a little thing here, a little note. Calculate time. Yeah, so we'll change the main code. Let's change this to quadratic data for our chart. And we'll change this to our call to quadratic time. Just got to take that and copy and paste it in each one. All right, and yeah, our calculation time is going to go up substantially. So we may need to comment out the other ones so this one can calculate without crashing our browser. But let's just wait and see what happens. Okay, so what's the main code for quadratic time? I'm going to rename const array here in quadratic time to const array 1 because I'm actually going to do const array 2 as well. And for const array 2, I'm just going to set up an array of numbers, say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Alrighty, and inside our main code, let's run a couple of for loops. And so let's do for let I equal 0, I is less than array 1.length, I plus equals 1. And then let's write another for loop inside that. So we have a loop inside of a loop. We can't use I because it's scoped. So let's do I equals n equals 0. And then while n is less than array 2 dot length, n plus equals 1. Okay. And then we, inside that for loop, let's just do if array 2 n is equal to array 1 I, let's just say const check. Actually, we do const same is true. So yeah, what do we do? So we go through each array, and for every item in this random number, go through and check to see if it is in this list. So in order to check, we have to go through each number in this list. So 10 items. So for every item, everything in array 1, we have to check it against 10 items. And then we set same to be true. So this is kind of useless, but I mean, this is not uncommon that you would see a loop within a loop. Oh, forgot an equal sign there. That would have caused a problem. A loop within a loop and then an if check. This is going to increase our calculation time dramatically. So let's go down here to quadratic time, and I want to see if this can actually handle it. So I'm not going to actually go to, I'll go to 10,000. So 100,000, I'm going to comment out the last 3 calls to quadratic time. And let's just see what happens here. I'm kind of fearful that the browser is not going to be able to handle it. Or, yeah, it's just going to time out because of the REPL's calculation time. I don't know if they throttle me if I'm using too much of their CPU time, but we'll see what happens. All right, so what happened? It actually ran. And actually, there's a zoom feature on the top right, so we can actually zoom in down here. Keep on zooming in, and we see that it plotted the first 3. Actually, the calculation time wasn't that bad. So let's plot out the rest of the 3. Let's uncomment those. And let's refresh here. And give it time to calculate. Oh, I need those open. That's calculating, so I can't click. Yeah, so as it's calculating, one thing that I can remind you of that everything in computer science, everything in programming hurts at scale. So the bigger your numbers, the bigger your arrays, the more painful it's going to get. So it's always best to test with a smaller number and go up from there. Okay, there we go. I'm going to inspect so we don't cache this. But what we see, actually, this plots out perfectly. So our constant time is down the bottom there. Our linear time is there, and our quadratic time is it's not linear growth, but it's a straight line, which is what we want to see, and it is substantially larger than our linear growth, which is what we would expect for two loops. And what is this 1,200? That's the milliseconds it took to calculate. So there's 100 milliseconds. No, there's 1,000 milliseconds, so 1 second, I guess, to calculate that. It must be the rest to draw it and render and do the calculation. But yeah, the performance time for this is actually it's worse. I mean, so that's your 2 nested loops. And so how would you arrange this code so you wouldn't have it? Well, you know, if you're going to do loops, try doing 2 different loops instead of nested loops. Essentially, if we say we had 1,000 items in our array, or 100 items, you know, if you have 1,000 items, then what you've just done is you've gone from 1,000 calculations in a loop to 1,000,000 calculations for 2 loops. So it's better to separate out the loops, have a for loop and then a for loop, and then you have, say, 2,000 calculations. Or in this case, if we had 100 items in our array, you know, we had to go through 10,000 calculations to get all this handled. If we did 2 loops, we'd have 200 calculations instead of nested. So, I mean, sometimes there's no way around nested loops, but if you can avoid them because they slow your program down. All right, that's quadratic time. Let's keep going. Next up is now we're entering the really scary zone, which is exponential time. And exponential time is represented by a big O of 2 to the power of n. So we take 2 and we put it to the power of the number of items we have in our array. So that'll be 100 items in the array. And so what's an example of this? Well, we have our Fibonacci sequence we did in an earlier video. So let's bring that back. Fib recur. And we'll pass in the number we're looking for. And if num is less than 2, return num. And then otherwise return fib recur n minus 1 plus fib recur n minus 2. Yes. Okay, and let's set up another function that's actually going through and handle the reporting of it. So let's go back up and grab our quadratic time. We don't need the arrays. We just need the start time, performance, end time, and update x and y. Okay, and I'm not going to put it inside function fib recur. I'm going to actually create another function that's called function exponential time. We'll pass in that num. And inside here, I'm going to paste that stuff we got from above. Let's keep our start time performance. We'll get rid of the main loop down to calculation time. Calculation time we'll update the chart to be exponential data. And inside the main code, let's put our call to fib recur, and we'll pass in that same number there. And remember, the number here is the position in the Fibonacci sequence. We want to find out the value of the that position, the Fibonacci sequence, that index position in that sequence. Okay, so for this one, let's do exponential time, and we'll pass in 10, exponential time 20, and exponential time 40. So when I did some tests on this earlier, exponential time, this calculation, I was able to get up to like 40 without my browser crashing. Anything over 40, I could get up to like maybe 45 even, but just to keep it, a power. So we did exponential time 10, and then we doubled it to 20, and then we doubled it to 40. It just works. I think it would graph well. Otherwise, we'll have some really weird points. Okay, so I'm kind of scared of what's going to happen here, but let's give it a shot. I'm not sure if this can actually handle the calculation of it, but let's... Oh, I did it again. I closed out the developer tool. Whoops. I'm going to bring that back. So we avoid caching. Why are we avoiding caching? If the browser caches the data, if it caches it can cache anything, it's going to slow down our calculation time, or it's going to increase it's going to lower the time it takes to do our calculations. Uh-oh, what do we got here? Console, n is not defined. Script at 152. 152. Should be num. Num. Okay, let's go back and run it again. Not going to close out the DevTools this time. Waiting, still waiting. We have another error. What's the other error here? Num items not defined. What? Oh, I know which one. Num items, exponential data, and num. Okay, that should be the last bug we need to fix. Still waiting, still waiting. It worked. Okay. So there we see constant time, linear time, quadratic time, and over here at this, we only have a couple of values. Let's see if I can do a box select. Whoops. We do box select here. What's that going to do? That's not just going to select the boxes. I want to try to, oh no, I got to refresh. I want to try to limit the scope of what we're seeing just to that first one there. But I think it, remember that the left side, the y-axis is graphing the time it takes to calculate. And given only 50 or the 50th position in the Fibonacci sequence, or 40th position, excuse me, we are already at the most expensive calculation we have seen thus far. And going back at our big O chart, that is here. Exponential growth. The only thing worse than this is factorial growth. And this would be if you're calculating like factorials. So, or like the traveling salesman problem. There's a number of problems that you would encounter, like map finding or path finding problems would be factorial. So that's the only thing worse than the Fibonacci sequence recursive. And why? Well, the recursive function, it has to calculate for every time that you are, or every number you're increasing, you're increasing the number of times that it has to split and then calculate again. So that's where the 2 comes in. We're essentially, because it's recursive and what's called a recursive tree with 2 different branches, every time that you run the recursion, it's going to split into 2. And we see that here under our recursive function, that it is splitting into, where did my recursive function go? Exponential time. Oh, right, yeah. It's splitting into 2. So then you have the split to the power of whatever your input is, how many times it's going to have to split. And so that's why it's exponential. How could you write this a different way? Well, I did a benchmark comparison between our Fibonacci recursion, writing it that way, and writing a Fibonacci sequence just using, let's see if I can make this bigger. Can I make it bigger? A little bit bigger. Just writing it as a loop instead of a recursion. And the recursive version, as we have it written, looking for the same position, the 5th index position, we see that the recursive version of it is 96% slower than the loop version of it. So recursive functions are elegant. I mean, very elegant, but you have to be careful of your recursion because it's a very expensive calculation. This is something that we mentioned last time, the expense that it's going to take to run a calculation. All right, the last one, the very last one, is going to be logarithmic time. And for logarithmic time, this is our binary search we did last time. So we're going to need our binary search that we wrote last time. Actually, binary. I'll just add this below. Binary search. And our binary search function, binary search, we had an array, we have a target num, and then we had let min equal 0. This is all covered in the previous video. Let max equal array dot length minus 1. Let counter equal 0. While min is greater than or equal, while max, I did that last time, didn't I, is greater than or equal to min. Counter plus equals 1. Const mid equals math dot floor. And then we had inside there min plus max divided by 2 to find our midpoint. If array mid equals target num, we return mid. And then otherwise, we did a check, right? Yeah. So to increase, if array mid is less than target num, we do mid equals mid plus 1. You could do plus equals 1. And then else, I don't know what that happened there. That was weird. Else max equals mid minus 1. Okay, and then let's do a function that's going to run that and calculate the time on it. So let's go up and we can grab our exponential time, everything here. Let's bring it on down to down here. Let's do logarithmic time, num items in the array. And okay, so we have a const start time main code. We'll get rid of fib recur in the main code. We'll go down to update x. Let's do logarithmic data, change num to num items, change that back to num items, change the next update y to logarithmic data. Inside the main code, actually, we're going to need to generate get our arrays. So let's do the same thing as before, const array equals create random num array num items 100. And let's set a random target every time it runs. Do math.round, math.random, and then let's only do up to 100. Okay, that's fine. Math.round, math random, that's fine. All right. So yeah, we're going to get a random target 0 to 100 and round. So it's going to round up or round down. Okay, and so let's go to our main code. And our main code's easy. Let's just do binary search. And we'll pass in the array above and random target as the target we're looking for. Okay, let's make our calls. This is the last call we're going to be making. So I'm going to go back up. I'm going to grab all of the quadratic ones we did because it's going to be similar to that. And we're going to change it to logarithmic. We're going to make a call to that. Logarithmic. Okay, that's good. I'm going to paste it into each one to replace quadratic time. And let's see, anything else we're going to do here? I think that's it. I'm going to comment out exponential time simply because we don't need it. And it's going to slow us down. So let's run it. Still calculating. So what is logarithmic time? Logarithmic time is what we covered last time with the binary search. Logarithmic is going to be the log of whatever number we're passing in. Max is not defined, 182. 182, while max, oh, let max, that was weird. Okay, learn it again. So yeah, logarithmic is equal to the log of it's base 2, so log base 2 of whatever number we were trying to get. Okay, so I actually had to go to my own computer to run this because REPL calculation time was taking too long. But it finished and it worked. And what we have here is actually all the, see if I can increase the size here. Will it automatically refresh? Let's see. Oh, I should have cached it. Silly me. Okay. I actually had to go to my own computer to finish the calculation because REPL was taking too long. But what we see here, it actually finished calculating up to 100 million and for each of the different ones. And what we see is we start to see that graph that we showed you earlier. This graph here, showing the different calculation times. And what we're looking at here is quadratic is up here. And then our logarithmic is right down here, right down the bottom. Big O of log n. And that right there is what we see down here, that logarithmic time is almost the same as constant time, which is nuts. So just going and accessing the first index in the array is the exact same time as it takes to process 100 million items in an array and to search for an item. So that is very performant. That is very, you know, would it better gone through a loop and going through for each item in the array? Well, we see what would happen. A linear time, which is the orange line above here, linear growth is actually taking much longer to search. And so if you're, you know, if you're waiting for, you know, if you're waiting for a web page to load for that calculation, you know, you want to make sure that, much like, you know, an engineer working on an engine would want to make sure that that's the right fuel and the oil is all there. And, you know, when you're writing code, you want to make sure that you're using the most efficient ways possible to accomplish your goal. You don't want to build a car with square wheels, and you don't want to do a search an array of 100 million items using a linear search, or worse, a quadratic search. So the point of all this is just to think about, and the more skilled you get, the more you do this. Do you start off writing a program and immediately say, oh, I know how I can make this the most performant? Maybe not at the beginning, right? But as you are going through, the easiest thing to do is remember, nested loops are very expensive. The more loops you have inside of each other, the more expensive it's going to take to calculate. So that's an easy thing to remember as a beginner. You know, the other things you can consider are going to be if your program is, you know, if it takes 4, 5, 6 seconds to calculate something, and you have 4, 5, 6 seconds, okay, fine, great. It's fulfilling the task, and you know, it's happening in what we call reasonable time. If you need something to load up in a web page and you need it to happen in just a few seconds, then, you know, 6 seconds is far too long for one calculation. So that way you want to look at making a faster way to process that calculation. You know, if you're doing microprocessors or drones or robotics, then you're going to want to find, they're already written in a fast language. JavaScript in the browser isn't the most fast way to do large calculations of data sets. There are other more performant ways to write it, or languages to write in. But you know, you try to find the solution for the problem that you're facing. And so now you have another tool in your toolbox to make that experience better, to make that code perform better. You can think about the efficiency of the code you're writing. And now I've given you ways that you can measure it against, or vocabulary that we might use to understand how it's measured against different ways of writing it, or what happens when you add in code. How much added time is that adding to your program? Things like what happens if you have like multiple different ones in the same program. So what happens if you have a problem that is, or a solution that is linear time, and some that's quadratic, and some that's logarithmic. And so in that case, usually you just sum all of it up and see what you get. And remember, you're doing it by the worst case scenario. So if the worst case scenario is quadratic time for any part of your code, then your entire program, your entire code is quadratic in its time signature. That's like the simplest, most easiest way to think about it. So yeah, but now you have a way of thinking about the speed of your programs and how you might reconsider them to make them a little more efficient. I know it's a long one, so thank you for watching. Hope it helped you understand program efficiency a little better, and I'll see you in the next one.